In the previous video, we had seen what was interpolation, and we looked into the process of adding zero-valued samples to increase the sampling rate. And if we are performing interpolation, I explained the fact that as a result of the interpolation operation, the bandwidth of the signal will be reduced by a factor of I. So if you look over here, minus pi to plus pi, the original signal was existing, and because of that factor I reduction, we have this reduced to minus pi by I to plus pi by I. And as a result, we can see that in this original span of minus pi to plus pi, you have additional signals that will be coming in, which will be like images of this particular original signal. So in order to restrict the output signal to the required bandwidth, we use a filter out here, which is like minus pi by I to plus pi by I, and we get the desired signal in this band. So as a result, after the sampling process, we add a filter out here. So this, even though it is mentioned as a low pass filter, it is basically acting as a low pass filter when we consider this span of the signal. But if we are to consider this half also, it should be in that band pass span. So if you have looked into the explanation that was given for FIR filter design, you would remember the fact that this diagram resembles a low pass filter in this span of minus pi by I to plus pi by I. So I hope you don't get confused by this concept of a low pass filter. So this low pass filter is basically referring to the fact that you're considering this span of the signal. Now moving on, we are going to look into the decimation explanation. So if decimation, interpolation was a process of adding sampling or adding samples, decimation will be the process of reducing the sampling rate or throwing away some of the samples as mentioned over here. So the ultimate reason for decimation will be to reduce the sampling rate at the output of one system, so that a system operating at a lower sampling rate can accept the signal as the input. So when we look at one more point that is being covered in this explanation is the fact that interpolation will require more complex hardware, and decimation will be requiring lesser hardware to implement a DSP system. So that is the advantage of using a system with a reduced sampling rate. In comparison, interpolation, in the case of interpolation, Fy was equal to Fx into I, and here if we are considering the decimation factor as D, Fy will be equal to Fx by D for this particular case of decimation. Now for this particular concept, we are going to look at this analysis part in a different way. So if Fy is equal to Fx by D, since frequency is inversely proportional to time, it would imply that Ty will be equal to Tx into D. So I hope you are getting this point. This equation is for the interpolation counterpart, where Fy is equal to Fx into I. But when it comes to decimation, Fy will be equal to Fx by D. I hope you are getting the difference between these two. Now in comparison, since Tf is inversely proportional to time, Ty will be equal to Tx into D. So if you look over here in the time perspective, what it means is that the time span at the output side will be increased, while the frequency span at the output side will be decreased. So based on the knowledge that we have already, we know that omega is equal to 2 pi f by fs, which is the sampling rate, and we are going to consider omega y. So omega y will be equal to 2 pi f by fy, and you know that fy is equal to fx by d. So this will be equal to 2 pi f by fx into d. So omega y will be equal, which implies that omega y will be equal to omega x into d, which would also imply that omega x will be equal to omega y by d. I hope you are able to get this comparison of the derivation. So we begin with omega y. Omega y will be equal to 2 pi f by fy, and 2 pi f, we substitute fy with fx by d, and when we do that particular operation we get fy is equal to omega x into d, and omega y is equal to, and similarly we come to the conclusion that omega x is equal to omega y by d, which is what we derive at this particular point. What we had learned as the part of the derivation earlier is that omega x should be equal to omega y by d, which means the signal at the input side omega x will be equal to the signal at the output side by d in terms of frequency. So this is the requirement of a decimation criterion. And now we are going to look at what happens to a signal when we consider the frequency domain analysis of this decimation operation. So what we see over here is that when this particular signal is subjected to decimation operation, the output signal of which will be generated will be consisting of a signal in this particular format. Now what does this equation mean? So if we take a look at this equation, basically what we can see here is if we are considering k to be equal to 0 to 1, if m is equal to 2, let us take as m is equal to 2, which is a decimation factor. So if m is equal to 2, we can see that omega y will be equal to summation k equal to 0 to 1 x of omega minus 2 pi k by m, which means when we expand this particular equation, it will mean that this will be consisting of two components, which is given by the summation, where k will be equal to 0 and 1. So x will be equal to omega. Now since k is 0, this part will become 0, so this will be omega by m plus x of, when k is equal to 1, this will become omega minus 2 pi by m. So which actually means is that this resultant signal will be combining or will be having two components which are separated by a span of 2 pi. So if you look over here, this is a signal that exists at omega by m. Now this is equal to omega minus 2 pi by m. So you can see that as a part of this operation, if we have a signal in this span, we'll be getting a signal which actually consists of two parts, or two parts of the same signal, or the output signal contains multiple versions of this original signal which is spaced apart in the terms of 2 pi. So this is centered at 0, this is centered at 2 pi, and if the next sample comes, it will be equal to k equal to 2, so it becomes 4 pi by m, which is what is shown over here. And you have these signals coming up over here. So that is a concept of this output equation. So basically what it means is that the frequency axis is compressed by a factor m. So if now let us look at it in this perspective. If our signal is supposed to exist in this span of 0 to pi, what it means is that it should lie, the input signal should lie in the span of 0 to pi by m. What is meant here is that if we know that omega x is equal to omega y by m, which is the decimation factor, and if omega y is equal to pi, it implies that omega x will be equal to pi by m, which is what is shown over here. This is a graph for the frequency version of x of the input signal, and this is a graph for the final output signal. So if this particular graph is supposed to exist in the region from 0 to pi, then this should be lying in the span of 0 to pi by m. That is a explanation out over here. And as part of what happens here is that this will be containing the shifted versions of this input signal at this part. So what it basically means is that the Fourier transform of the output signal y of n is a sum of m uniformly shifted and stretched versions of x of e raised to j omega scaled down by a factor of 1 by m. So that is a point being conveyed over here, and I hope you have got this with respect to the graph. Now what will happen? Now the basic condition out here is that if this is to be restricted in the range of pi, the input signal must be restricted to the range of pi by m. That is a basic concept out here. Now what happens if this goes beyond pi by m? If our input signal is going beyond pi by m, what it means is that the output signal will also have the similar expansion which will go beyond pi. So if you look over here, this particular signal is supposed to be existing in the region of pi by m. But since it has gone out, the output signal will also be creating the alternate versions which will be overlapping with each other. So if you look over here, this one component is there which goes up to this point. Then you have another component which is again expanding to this side, the left side as well as right. Here this one also expands to the left and the right, and similarly you can see that this creates an overlap of the signals out here, and this is known as aliasing. So what is required out here? To avoid this problem of aliasing, what is required here is that, and what caused aliasing out here actually, when the input signal went beyond the pi by m range, it resulted in this overlapping effect which resulted in aliasing. So our aim should be the input signal must be restricted to pi by m. So what we actually do here is we place a filter first at the beginning, and if previously we had anti-imaging filter, this filter will be known as anti-aliasing filter. So what is the job of this anti-aliasing filter? It will be restricting the input signal to the span of pi by m. And after that, we carry out the downsampling process, which means when we carry out the downsampling process, we get an output signal like in this version that is drawn over here, where you don't have that effect of aliasing. So that is the frequency analysis topic with respect to decimation. And I hope these two videos help you to understand the topic in a clear way.